What is up? What is up, people? It's been a while since we posted our last video. It's been a month almost. We didn't post for biophysics because we didn't understand the shit ourselves. Uh, but proud of my brother Mateen, the other quantum duo guy. He did really well in his biophysics exam. I didn't. It was pretty hard for me. So that's why I don't want to make videos, because if I didn't know what I was doing myself, I don't want to make videos. But it doesn't mean that because of making medchem videos that I'm god or something in medchem. I just feel like I teach better when I teach I learn better, so that's why I'm making these videos, mostly for myself, also for you. I hope you guys benefit from this. So before I jump into this, I hope a lot of you have a background in the organic chemistry. If not, go over to YouTube, go over to the channel The Organic Chemistry Tutor, and watch his introduction to organic chemistry video. It's a bit long, I know, but come on, put some effort in. You're in dental school, you chose this degree, it's gonna be hard, you knew it. Go put some effort in, okay? It's not always gonna be easy. So go try, put some effort in. So let's get in, and first off, define what an organic compound is and what an inorganic compound is. Simple definition, okay? Compounds which contain carbon as well as hydrogen and are obtained from living organisms. Fine? So what's the requirements? It's supposed to contain carbon and hydrogen and needs to be obtained from living organisms or substances. That's why we're learning this stuff, okay? If organic chemistry wasn't derived, or organic compounds weren't derived from human bodies or living things, we wouldn't need to learn this. But since we're going to become the best doctors and the best dentists ever, we need to know. So let's move on. Let's start. Clearly, you can see over here the answers are already given. I would prefer that they weren't given. I mean, I could if I wanted to put white paint and all that shit. I don't want to do that much work. Please understand. Whatever. Clearly, CH4 has C, has H. One more thing. The C and H should be bonded covalently. And they should be bonded. If there is no C and H bond in your compound, it's not organic. So if you don't clearly see this, if you don't see it with your big googly eyes, if you don't see it, it's not organic. So let's see. Organic, clearly. Inorganic, why? Because there is no C. Oh no, shit. This is the structure. Okay, whatever, I'm not drawing the correct structure, whatever, just there's no CNH. There's no CNH, it's not organic. This is clearly organic, C2H2, clearly organic. Now, two things where you might be confused is this thing over here. Clearly there's H, clearly there's C. Why is it inorganic? Okay, let me tell you. The structure of this goes something like this. Go C over here, double bond O, single bond O, O, boom, boom, H, H. So that's the structure of H2CO3. Clearly you can see the carbon is not bonded to hydrogen in any way. So that's, do you need anything else? Do I need to say anything else? That's the reason it's not organic. Because there is no carbon and hydrogen bond, not organic. Get you in your head. Okay. Same thing here, the same structure as this, but instead of one H, it's Na. So yeah, hope this was pretty simple. Let's move on. Hybridization. This is my favorite thing to teach people, because it's like they don't really know how to do it, but when I give them this trick, they're just like, wow, this shit's easy. Yeah, so let me tell you. The stuff, this one you're supposed to know. Now, first let me tell you, how do you identify, like if I tell you just randomly, what's the hybridization of this? How do you identify? So let me give you my system. Let me give you some secret sauce. It's definitely not a secret. This has been going around on the internet. I learned it from the internet, so just gonna pass it on here. Now, look at this. A single bond is a point. Just listen to me. Let me cook. Okay. So a single bond is a point. A double bond is a point. A triple bond is a point. Don't be confused. Don't think, oh, what's point? I'm just saying like a score or something like a point. Just wait. I'm gonna explain why. And a lone pair is a point. A lone pair is a point, not a single electron. That's not a point. So single bond is a point, double bond is 1 point, triple bond is 1 point, and double bond is 1 point. Now look at this. Now look at this. Now let's look at this carbon right here. It has 4 single bonds. Okay. So how many points does it have? Clearly 1 point because of this, 1 point because of this, 1 point because of this, and 1 point because of this. 4 points. And that's the maximum it can have. So when you have 4 points, it's sp3. If you have 3 points, it's sp2. If you have 2 points, it's sp. Okay? Get in your head. Come on now. Single bond is 1 point, double bond is 1 point, triple bond is 1 point, triple bond is 1 point, and lone pair is 1 point. Again, don't say double bond is 2 points. No. Okay? So yeah, if you get a score of 4, that's sp3. Score of 3 is sp2. Score of 2 is sp. Now let me go on to some complicated compounds and you understand. Here, this clearly has 1 bond here and 1 bond here. So 1 point here, 1 point here. So it's sp, right? No, it's not sp. Let me tell you why. First, you have to look at the periodic table. That's why I have it ready for you guys. See me? I got it ready for you guys. And I'm playing no games. Okay, whatever, bros. What the hell is wrong with me? It's late. I want to sleep. It's not very late. It's like 11 o'clock night. Just came back from the gym. I'm very sleepy. I want to sleep. I just took a nice hot shower. I want to sleep. But I said to myself that I'm going to make the video. So I'm making the video. Whatever. So let's start. So going from left to right. This has 1 valence electron. This has 2 valence electrons. Skip all of this. This has 3 valence electrons, 4 valence electrons, 5 valence electrons, 6, 7, and 8. This is the number of valence electrons. What's the valence electron? If this is the nucleus and this is its shells, the outermost shell is the valence shell, and the number of electrons in the shell are called the valence electrons. So what I wrote right now, 1, 2, 3, 4, 5, 6, 7, 8. This is the number of valence electrons. Remember this, and I'll tell you how to use it now. Now, we were solving which question? Oh, let's look at the oxygen right here. So how many electrons, valence electrons, if we say it has? 1, 2, 3, 4, 5, 6. Clearly, oxygen has 6 valence electrons. So let's draw that out there. So we have 1, 2, 3, 4, 5, and 6. Now, every bond, a single bond, is an electron basically. So over here we have 1 electron and 1 electron which create a bond. Okay. So oxygen, while forming this bond, is giving 2 electrons. So 1 electron's here and 1 electron's here. This electron over here is not contributed by oxygen. The electrons given by oxygen are these 2. Okay. So we know it has 6. Okay. 2 are taken. 2 are taken. So we got 4 left. 2 are taken and we have 4 left. So 4, we pair them. Boom. Just like that. So clearly we can see that it has 2 lone pairs as well. So let's count the points again. 1 single bond, so that's 1 point, 1 point. And a lone pair is 1 point, and another lone pair is another point. So total, That's 4 solid points. So that's sp3. Boom. Of course I'm right. Okay, whatever. Moving on. Let's look at this one. Let's look at this. This one's a little bit SH. Again, since we're looking at this, let's look at how many valence electrons S has. S is right here. Let me come back. 1, 2, 3, 4, 5, 6. Same like oxygen, it's got 6 valence electrons. Let's go back. So let's draw it. Clearly, we know one of these electrons is taken up in the bond. So one electron, let's cut that out. Another electron taken over here in this bond, because SH is not an element. S is an element and H is another element. So clearly it's forming a bond here. So 2 electrons are gone. Now we're left with 4. So clearly pair them up. Boom, boom. So we go 1 lone pair, 1 lone pair. That's 2 points. 1 bond here, 1 bond here. That's another 2 points. A solid 4 points, which gives it sp3. Understand? Look at it over here. What do we see here? We see 1 bond, 2 bond, 3 bond, 4 bond. Clearly sp3. Simple. Where can I make this a little bit okay? Let's do this. But like this is pretty simple. Please remember again. 1 point for single bond, 1 point for single bond, 1 point for single bond. So that's 3 points already. Now we have this double bond. If you're stupid and you say that this is 2 points, I'll slap you. It's not though. It's 1 point. As I said, single bond is 1 point, a double bond is 1 point, and even a bloody triple bond is 1 point. Okay? So yeah, I hope using this, you should basically be able to identify any hybridization for anything. Now, sorry. Rotation about carbon-carbon bonds. This is just, I hate how they have structured this, because this is just them randomly throwing like info all across. They don't even care if it's related to each other or not. They're just like, oh wait, totally forgot. Rotation about carbon bonds. Let me throw that in, and they throw it in. So it's not really related. But yeah, let me just explain this to you. Now, I would want to use this board. I did invest in some markers, but I don't think they bloody work. So whatever. Now, let's make it simple. Okay, a single bond. Okay, when it has a single bond like this, like over here. Okay, a single bond, it can rotate. You can see my pen, it's rotating. Okay, boom, 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 boom. It's not a big problem. What do I mean by this? So you see, let's say C, H, 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 and single bond C, Cl, H, and in H. This is the molecule. Now let's say I spin this. Okay, I spin this, and now I have this. Now clearly you can see the Cl is now down and this over here is up. So some of you may think that this is a whole different molecule, but it's not. It's the same thing. It's identical, just that it has rotated. Now this can only take place on a single bond, because a single bond is made of what? When we have a single bond, it's a sigma bond. Sigma bond. When we have more than one, we get into the pi bonds. So a double bond is 1 sigma bond and 1 pi bond, and the triple bond is the same. It contains 1 sigma bond and 2 pi bonds. Okay, so the pi bonds, what they have is the pi orbital, the p orbital, which is somewhat shaped like that. So what happens when there's a double bond over here, as you can see, is there's no rotation. Why? Because this is the same structure as this, just displayed to us like this. You can see that this is a p orbital which is empty, doesn't contain anything. Why? Because it's an empty orbital. Why? Let me tell you why. First of all, tell me what the hybridization of the C is. Tell me. Do you have it in your head? Hope you said sp2. Okay, so if you said sp2, that's pretty good. If you said sp2, we clearly know that we can go up to an sp3, but this hasn't gone up to an sp3. So clearly there's a p orbital which is lonely and sad and alone. So that p orbital, as you can see, is over here. It's empty, but it's there. Now what happens is we have two of our atoms like this. Now over here, when we're looking at it on a nice seminar slide, clearly the bond length is huge, but bond lengths aren't usually this huge, okay? They're super tiny. Of course we can't see them, they're microscopic, they're so small. The bond lengths are absolutely microscopic, they're so small. So what looks to be on the diagram slides, the p orbitals, these are the p orbitals, to be this far, in actuality they're like that close. Okay, so what ends up happening, these things, they fuse. So what happens is, over here you can see it's a long overarching fuse, but it doesn't look like this. What it actually looks like is more like, see how they're fused now, the p orbitals have now fused. So what happens is, now the fact that they're fused locks them, basically like a lock. So let me try to make this as the example. See this? You could spin this. It's a single bond. You could spin this. But let's say I have a double bond. If I were to spin this, okay, from one side only, I mean, of course I could spin the whole thing around. But if I were to spin it from one side only, check this out. See how it knots up? You don't want that happening, okay? And that's exactly what happens, and this is exactly what happens, and this is exactly why you cannot spin or rotate about a double bond. Understand? It's like a knot. So these are the two bonds, and see, knots up. You cannot do it. Okay? This is why you just think about it like that. Done? Random bit of information there. Boom. Threw that in. Okay? Now, let's look at hydrocarbons. What's hydrocarbons? Pretty straightforward. Hydro is hydrogen, carbons is carbons. So a molecule which contains a compound, or a molecule which contains hydrogens and carbons, only hydrocarbons. They have two groups, aliphatic and aromatic. Aromatic are made of cyclic unsaturated hydrocarbons. Now, before I go on, what's saturated, what's unsaturated, what's this new terminology? Pretty simple. Listen. Saturated is carbon and hydrogen, all single bonds. Single bonds only. Okay? When you have only purely single bonds, a very simple structure, a structure which you can look at and understand, all single bonds, that's saturated. Okay? If there is another bond apart from a single bond, like a double bond, a triple bond, it's unsaturated. Okay? Understand? Now, cyclic unsaturated hydrocarbons are specifically aromatic. Okay? Aromatic means smell. Doesn't have to be a pleasant smell. Could be bad, whatever. But cyclic unsaturated hydrocarbons are aromatic. Now you can see over here, in aliphatic we have saturated hydrocarbons and unsaturated. Clearly you can saturated have single bonds only, and unsaturated have double bonds, triple bonds, whatever. Now you can see over here, this is cyclic saturated hydrocarbon, so that's not aromatic. Exactly. Okay. Now ask over here, what is the typical hybridization of state of carbon in these compounds? You tell me, what's the hybridization of this? So I hope you have the answer. It's sp3, because boom, 1 point, 1 point, 1 point, 1 point, total of 4 points, which is equal to sp3. Over here, boom, 1 point, 1 point, 1 point, 1 point. So for this, sp3. For this, sp2, because 1 point, 1 point, 1 point. So sp2. For this, sp, because 1 point and 1 point, even though it's 3, 1 point. So sp. Over here, we see 1 point, 1 point, 1 point, 3 points. So that's sp2. Similar over here. You all should know this shit. So fine. Now what else do we have? We have, yes, over here. Functional groups. What are functional groups? How do we? What are functional groups? So groups of atoms within a molecule that have a characteristic chemical behavior. Okay, now let me look at this. Look at this chart. R is a hydrocarbon. Could be anything. Could be any hydrocarbon which we discussed over here. Could be any one of these. Okay, that's an R. Now, what is a functional group? It's a set of, what does it say? A group of atoms which join at the end of a group, like a compound. And so basically, I'll tell you what these people are like. It's like, you have a friend group, nice friend group with a few people in it. You guys have been thinking the same, all of that, okay, whatever. You guys have a nice strong bond. Enters a new friend which all of you are not familiar with, but now this guy is an alpha male, okay, big strong alpha. I don't know what I'm trying to say, but listen, what he basically ends up doing is influencing your whole friend group into behaving like him, okay. So what's the functional group in this? That guy who came in, he's the functional group. He came into your group and made your whole group behave like him. So what this guy does is he goes around groups and makes everyone think exactly like him. This guy is like that. That's what a functional group is. So as soon as it's attached to a compound, no matter what compound it is, okay, it could be, for example, looking at this R, let me say CH3Cl, or I say C2H5Cl, or C3H, no, C2H3. No. C2H4, C2H5. I'm sorry, C2H5, C2H5, C3H7, Now, the fact that all of these three things have Cl in them will make all of these three behave the same. Okay, so no matter whatever the compound is, if they have that functional group, you can tell, okay, fine, this guy has that functional group, so he's gonna behave in this way. Okay, that's what it's for. Now this chart, I mean, like, how do I even explain this? You just have to learn this. Brute memorization. Somebody make flashcards, whatever, learn this, put this inside your head. I cannot do anything. I can't just be like, oh, this is Rx, this is the halogen, this is the halide. I mean, there's no explanation. It's like, why are you named your name? Why am I named Arham? Because I understand. What do I explain? So this is like that. Just have to learn, okay? Same for this page. And then identification. Identification, again, I would do this, but the questions that they ask me here are absolute jokes. Alkene because it's a double bond. Okay? Alcohol, OH. Okay, fine. Let me just explain this to you. What's an alkane, an alkene, and an alkyne? An alkane is a saturated, no, a saturated hydrocarbon. Okay, basically contains CNH, single bonds only. So CH3, C2H5. And how am I creating this? There's a formula. It's basically CnH2n plus 1. I think this is the formula. Let me just confirm. Crazy. Sorry guys. Sorry. So sorry to want to do that to you guys. CnH2n. So alkenes, and alkynes. Okay. So the formula for this is CnH2n plus 2. I think this is CnH2n and this is CnH2n minus 2. Should be. Let me check. Don't want to mess up again. Just alkyne formula. Boom, I was right. As you can see over here. Whatever. So yeah, what is this? What's an alkene? An alkene is a carbon hydrogen compound with a double bond. And an alkyne is the same thing but with a triple bond. Okay? To write their formulas, now you guys must know that 1 carbon is methane, 2 carbon is ethane, 3 carbons is propane, 4 is butane, 5 is pentane, 6 is hexane, 7 is heptane, 8 is octane, 9 is nonane, and 10 is decane. This is the number of carbons. So if I were to say what's an alkane with 3 carbons, so C3, you're going to write that, and then for an alkane the formula is H2n plus 2. So H2n is basically 2 times 3, so that's 6 plus 2 is 8, so C3H8. So that's propane, understand? Same thing applies for alkene and alkyne as well. I just said this because some people don't know, some people don't, so that's why. Other than that, it's basically you learn this, you look at this, you're like, oh okay, what do I remember? Basically that, nothing else to understand. Again, one of those informations where they just throw it in randomly, predict the presence of a dipole moment in the following molecule. Now see, a dipole moment, if it's an unsaturated, or if it's just a hydrocarbon, pure hydrogen and carbon only, a compound contains hydrogen and carbons only, you can be 100% sure that it's non-polar. It doesn't have any charges. What's polar? I have to explain this as well before what's polar? Polar is basically a positive and a negative, of charge difference. Okay, so when like in a magnet, one side's positive, one side's negative, so this is a polar. It's a polar magnet. Okay, same way, sometimes this electron is negative, proton is positive, so this total is like polar. Understand? Okay, so now in polar, when you say polar, something like this happens. Okay, now Cl, now look at the periodic table again. We know that electronegativity increases left to right. This increases. Okay, so let me draw an arrow which looks like that, so it shows that it increases. Okay, from left to right. Clearly Cl is in the far right, so its electronegativity is pretty high, especially, no, not especially, wait, let me check, compared to hydrogen, especially because hydrogen is all the way back here, so clearly it's way more electronegative. But to carbon, it's just a wee bit, but it's still more electronegative. So what ends up happening is, because it's more electronegative, what is electronegative? Electronegative means the ability to attract electrons. So what it does, Cl, since it's more electronegative, it attracts electrons towards it. Now we know that in a covalent bond, electrons are just moving around from one cloud to another. You see clouds like this. Okay, these are the clouds, electron clouds, where the electrons reside. Now, because the chlorine has a higher electronegativity, it attracts electrons more. But that doesn't mean that it just pulls all of them towards it and just keeps it on. It's just that the electron cloud near chlorine becomes bigger. So basically, the chances of finding an electron around Cl is much higher than finding an electron here, because the fact that this attracts electrons more, the electron cloud increases, and because it attracts electrons more, that means it has electrons around it all the time. And because it has electrons around it all the time, it adopts or it portrays a negative charge. But you can't like look at it and just say, okay, that's a hard negative or a hard positive charge, because it's not. It's just a slight little thing which happens. So that's why we use this symbol over here, which represents partial. So we can say it's partially negative and partially positive, where it's referring to the C, and this is the partially negative referring to the Cl. This is how you predict. Now, how do you predict? Let me just look at this now. Look at this. Clearly, same thing. All of this, if it was the same. Now look at this one. Now this molecule, you might say, oh, since it's going one direction, this direction, this direction, this direction, all of the electrons being pulled that direction. Since they all have like this symmetry, they should cancel out, and hence it's nonpolar. Doesn't work like that. Don't use your brain. Listen to me. Now, clearly, the electron clouds are looking something like this. They're pretty chunky around the Cls, but around the carbon is pretty less. So what happens? Obviously, these obtain a partially negative, partially negative, partially negative, partially negative charge, and our carbon obtains a partially positive charge. Clearly, due to the presence of more partially negative charges, the overall molecule is going to be negative in charge. That's something you just need to know. Over here you can see clearly all of that. Oxygen as well, you can see it's a pretty electronegative right there. Compared to carbon, still it's little bit, but it's still electronegative. You have to consider it. Over here, pure just carbon and hydrogen, so it's non-polar. Explain the effects of functional groups on physical properties. When we are, I think this one, when we are going with the third and fourth lecture, that time I can explain it a bit better, but not now. This question, interesting. Many people confuse themselves. What's the use of having a strong bond? What's the use? Why care if I have a strong bond or not? It's the strength of the bond is very much indicative of your boiling point. Basically, what I'm trying to say is, the more stronger your bond is, the higher your boiling point is. Now, clearly over here, we can see, because this is polar, it's going to have dipole-dipole forces. Intermolecular forces are going to be dipole-dipole. Now, if we don't know what dipole-dipole and all of this shit is, go back to my intermolecular and intramolecular and intermolecular forces video. Watch the first bit. I've explained very clearly what intermolecular, intramolecular, ion dipole, London forces, covalent bonds, ionic bonds, everything. Go ahead and watch that video. But since it's polar, it's usually supposed to have a dipole-dipole bond, which is way stronger than whatever this shit has, which is London forces. So why is it that the bloody boiling point is so similar? Shouldn't this be a higher boiling point and this should be like a lower boiling point? No, because I've said this before in my general chemistry videos as well, but boiling point is directly proportional to mass, molar mass, and of course strength of the bond. Okay, so the more molar mass you have, even if you have the shittiest bonds, if you just have a higher molar mass, then you're gonna have a higher boiling point, as you can see here. They might ask this very tricky questions. They can ask this in MCQs. Hello. Hi, Shreya. Yes, I am. It's okay. Why? What do you want? Do you want anything? Oh, no, okay. Yes, okay. One of the students just interrupted the video. Shout out to Shreya. Just came through. But let's continue. Identify whether the following molecules are polar or non-polar. Let's run through this shit. C and H only non-polar. C and H only non-polar. C and H not only has also OH. O is clearly more electronegative than C, so polar. O, as I said, C2H4, CNH only non-polar. CH3Cl, Cl3 is present. Cl3 is more electronegative than C, polar. CH2Br2, polar because of the presence of fucking Br2. Sorry, I swear. Okay. CH2F3, polar, of course, polar. Okay. Pretty simple. Should be pretty simple, guys. Now, this London dispersion forces. Now, since it's not polar, non-polar usually exert London dispersion forces. What's London dispersion forces? I don't want to explain the whole thing again. Go back, go to the video. Go to that the intermolecular and intramolecular forces video. I promise you I've explained it very well. I don't want to just waste my time again, okay? So yeah, OH, explained this as well. Explain all of this hydrogen bond. Please go watch that video. It's pretty nice. It's the same thing. So understand this, so you'll understand how to identify everything. So go watch that video. Very good. Now don't get angry at me and be like, oh, you should have just explained it. Why are you telling me to go back to the video? Because I've already made the video, okay? I know some people who are just going to be like, oh, you should just tell us. I'm talking to Mira, okay? I know, but go back to the video. Just put some effort in, okay? Yalla, moving on. Inductive effects and mesomeric effects. This is pretty important. Okay, let's start and continue with the inductive effects and mesomeric effect. Again, it's one of those little information that they just throw in the middle, no relation, no, like, you know what, if you want to, you could have a whole lecture on inductive effects, mesomeric effects, but no, just randomly throw two slides in there. Like, I don't understand who made these slides. What was he smoking? I don't understand. But let's move on. What's inductive effect? I already told you this. I did. But you didn't. But I didn't tell you that this is an inductive effect. When I was explaining to you how polar bonds become polar, I said what? That let's go to the shit there. Yeah. What happens over here? There's a covalent bond made over here, which is a single bond. So as a single bond, I said which bond is it? It's a sigma bond. Specifically, a single bond is a sigma bond, right? And inductive effect specifically takes place in sigma bonds. Okay, listen to this now. Now, what happens? The electrons move towards the chlorine atom. Why? Because it's more electronegative, and they kind of like, they don't leave, but they stay more away from the carbon atom because chlorine is just so attractive, you know. So that's why the electrons are more to be around the chlorine than are this thing. So what happens basically, this electron, let me just show you the example that they have given us over here. Over here you can see inductive effect. So clearly there's two types. There's electron withdrawing, okay, and electron releasing. What does this mean? Look at this. Clearly, partially, this is the bond. C is attached to X, and like I explained how a partially negative and a partially positive charge is produced. I explained. So this movement of electrons towards the more electronegative element, okay. Again, remember guys, it's not that all the electrons just camp out here, all of them are just sitting here and none of the electrons are here. It doesn't work like that. It works in clouds. We're in university, we can't be speaking in like, you know, oh, electron just goes and sits there. No, it doesn't work like that. It's more like, you know, clouds, where this is probably how the cloud is. The electrons are free to move anywhere in this cloud, but as you can clearly see, they prefer to be around the X because it's got a higher electronegativity, okay, and that's why it shows a negative charge. Now, since this guy is pulling the electrons towards it, this is an electron withdrawing element or electron withdrawing group, okay, and we have a few examples, and this we should learn, Okay, I don't know about NR3, but this, guys, you need to learn. Because later on in these lectures, these things are they're gonna come up and they're gonna be very important. So remember this. What are the electron withdrawing groups? Basically, which electrons, which elements, or which group of elements pull electrons towards them. This is very important, guys. Again, I'm telling you, very important. Learn this. Okay. Same way, electron releasing. It's opposite over here. If this is pulling, if they are withdrawing, then this is releasing. Simple. We have a few examples of that as well. Basically, groups which freely just give their electron. They're like, okay, fine, I don't really want it. If you want, you can just keep it. They give it up. They don't really care. We have O, need to learn. COO, need to learn. Okay. Alkyl groups. What's alkyl group? Can be an alkane, an alkene, or an alkyne. All of these come inside alkyl groups. They are also electron releasing, electron donating, whatever. NH. Need to learn this. Now, there's another form of this which takes place. And usually you must have heard it in class. It's called resonance. Is the delocalization of electrons. What's delocalization? If I were to stay where I stay in Bahrain, I live in Bahrain. If I was to stay in Bahrain for my whole life, I would stay there and I would become a local. I'm staying locally. You understand? I'm just trying to give you an analogy so you can remember. Don't come after my English, okay? So if I live there in Bahrain my whole life, I'm a local. I live locally. But if I try to travel and move all around the world, I'm delocalizing. That's basically what the electrons are doing. They're not sticking to one orbital, like a p orbital or something. They're moving around. Okay, so that's called delocalization. Now, this effect, the resonance, has a little. A resonance effect has like its branches. One of the branches are mesomeric effects. Okay, what's this? The transfer of pi electrons or lone pairs. Clearly, it says pi electrons. So for that, what do you need? You can't work with a single bond because a single bond is sigma. So for pi electrons, you need a double bond. You need a double bond or a triple bond, whatever. So clearly you can see in mesomeric effects, all the elements, they will have a double bond. Will. Have to. Can't work. Get me? That's how that works. Then clearly you can see that. And same way, you can see over here, there's a minus I and plus I effect. Electron withdrawing, we had learned before, an inductive effect is minus I effect. Basically, when you're pulling, you become more electrons towards you. You have electrons all around you, so you become negative as well. So that's called minus I effect. But when you're releasing electrons, when you're releasing negative charge away from you, and you're becoming more of a positive person, that's a plus I effect. So minus I, plus I. Same way, there's minus M and plus M effect. So this, you can relate it to inductive effect as well. Clearly, you can see the decrease in electron density from the rest of the molecule. So what happens here? We have one group over here attached. Okay, because of this group, this whole molecule loses electron density. Why? Because it's pulling electrons this side towards it. Now you may ask, why is this not inductive effect? Because I said this is basically the movement of pi electrons. Okay, this is the mesomeric effect. So it's basically the same thing, but taking place in compounds with double bonds and triple bonds. Okay, so I hope that is enough to understand this. Again, minus M is basically this O is attracting electrons towards it, so it has more electrons towards it, making it negative, so minus M. Over here, this Cl, what it's doing is, this is not a reaction arrow. Please don't think that it is a reaction arrow. It's a bond line which has an arrow representing the attraction of electrons. But since it has too many electrons, what this does is it donates basically plus M effect known as electron, increasing the electron density of the molecule. And this need to learn. I don't know how I can remember teach you this, but you have to learn it. Just learn it. Types of reactions. There's substitution, there's addition, there's elimination. Okay? What's substitution? Okay, let's say substitution is I am adding this Apple Pencil to these two markers. What have I done now? I substituted the blue marker for an Apple Pencil and I kicked this shit out. So this is a substitution reaction. So where you just switch things around while the whole thing remains the same. You can physically look at it and be like, oh, okay, this has just been moved around a bit. That's how you can say that substitution. I mean, of course, not exactly that, but you're getting the general gist of it, okay? Additions, very simple. You have two or more compounds, they join and they become one. Simple. Eliminations is a bit different. See, eliminations is you usually have like one and one, like one compound and another compound, but you can clearly see that something has been removed from it. Okay, so let's look at some examples and then we can understand. Look at this. Two compounds become one, addition. Okay, now over here you can see Cl and OH have been switched together, so substitution. Okay, over here you can see what? You can see what? The H which was here. Because there's, remember, in skeletons we don't write the H's, but they're there. So the H which was here just got replaced by CH3 and this H joined with HCl. So we got this and this. Quick question for you guys who know. What's this compound called? If you didn't know, it's fine. I'm going to teach you later on. But it's called toluene. Benzene ring with CH3, toluene. Now, two things become one, addition. Simple. Substitution, how? There is an H over here which was replaced by NO2 and NO2, substitution. Okay. Addition, two things become one, addition. Substitution over here as well. Why? Because you can see CH4, one of the four H has been replaced by a Cl. So that's why. It's pretty simple, I hope. Okay. Now, what's cleavage? Over here it says describe the cleavage of covalent. Cleavage. Know what you guys are thinking right now. It's not that. It's definitely not that. If they had showed that, that would have been amazing. But yeah, there are two types of cleavages. What's cleavage? Breakage. You're breaking something. You're splitting something. That's cleavage. Okay? That's cleavage. Now we have homolysis and heterolysis. So homolysis is a type of cleavage where, as you can see over here, it usually takes place between elements or compounds like, Br2, F2, Cl2, where they're two non-metals which have equal electronegativities. So what happens when they're splitting, okay, they both have the same electronegativity. So when they're splitting, they both attract the electrons the same amount. So what ends up happening is they both have the same amount of electrons left. If they shared electrons to form a bond, while splitting, they keep their electrons because they both attract the electrons the same amount. So this basically creates a radical. If it was a lone pair, it wouldn't be called a radical. Since it's one electron only, it's called a radical. Clearly, if it's represented like this, it's a radical. You will understand. They'll be represented like this is a radical. In heterolysis, what happens is one of the atoms, like I said, will have a higher electronegativity. So while splitting, what happens is this guy will take more electrons while splitting. Okay? So by doing that, it becomes an ion. Like I said, this is a negative ion, positive ion. Okay, I hope you understand that. Okay, electrophiles and nucleophiles. Now this is coming in. This is the addition, elimination, substitution, and an electrophile, nucleophile, they're all gonna add up to form something. Let me teach you that. Electrophile. Now, we have had this word before and I've explained this word before as well. Phile. What's the meaning of phile? Phile. It's to love. Pedophile. What's a pedophile? Pedo is children, like pediatrics, whatever. Phile is love, who loves children, whatever. Okay. An electrophile. What's an electrophile then? What electro is electron and phile is love. So whatever loves electrons is electrophile. And what's a nucleophile? Whatever loves a positive charge. I know it should have been a proteophile or whatever, but I don't know why they made a nucleophile. I don't know why, but they made it like that. So what's a nucleophile? A nucleophile is something which, if it's positive, I'm attracted to it. I love positive. So to like negative charges as an electrophile, I am an electrophile. If I am to like a negative charge, what does that say about me? It says that I am positive because opposites attract, remember? Same goes for nucleophile. So you can see an electrophile has a positive charge, always partially positive or net positive, whatever. A nucleophile has a negative charge. Okay. Now over here, let's identify nucleophile. Clearly, H2O. Okay, H2O. So what happens here? O and H2. Okay, sorry. Clearly O is more electronegative than H, so it attracts more of the electrons, creating a partial negative. This is a partial positive and this is a partial positive. Is that to be right? That is right, yeah. So it has more electrons around it, but also remember, electron has oxygen have lone pairs. So the fact that it has lone pairs and the fact that it's attracting electrons towards it gives it a heavy negative charge, which overpowers the partial charges of this. That's why it's a nucleophile. Okay. This clearly it's a negative charge, so nucleophile, clearly positive charge, so electrophile. This should be pretty straightforward. NH3, so NH3. Nitrogen is more electronegative, so it's going to attract more electrons, so it goes like that. So this will have a partially positive, partially positive, partially positive, and this will have a partially negative. You can see that the amount of wait. No, I'm just confusing myself. No. It is a nucleophile. You might say that it has more partially positive charges. But the fact that N also has, like I said, lone pairs. So lone pairs, along with the fact that it attracts electrons, gives it a huge negative charge and overpowers all the other partial positive charges. Now, this is a simple question. Whatever. Now we know what substitution, addition, and elimination is. Now we know what an electrophile and a nucleophile is and what a radical is. Combine all that knowledge to get questions like this. So electrophilic can have 3 branches now. What are those 3 branches? Some weird ass noise at night. It's weird. Substitution of electrophile, addition of electrophile, elimination of electrophile, and then nucleophilic, the same thing. Substitution, nucleophilic, addition, nucleophilic, elimination. Let's look at this. We know this is an addition reaction. How do we know that this is a nucleophilic addition reaction? Because we know that this is a nucleophile. How do we know that this is a nucleophile? I'll tell you why it's a nucleophile. It's a nucleophile because what do we see attaching over here? Attaching to our carbon atom over here is Cn. So when we split this, what do we get? We get H plus and we get Cn minus. So we see clearly a minus guy has attached to our C. So if it's minus, then it's a nucleophile. Remember, if it's minus, it likes positive charge, nucleophile. So clearly it's nucleophilic addition. Now, you already know how to identify addition and all. You just need to identify if it's a nucleophile or an electrophile. Looking over here, clearly negative charge, so it's a nucleophile. It's blatant. Now over here, CH3Cl, what gets added? CH3 gets added. CH3 gets added, okay? So over here, CH3 plus Cl minus. Since the plus gets added over here, plus is an electrophile, so that's why. Now over here, HCl is split. So what do we see is being attached over here? We see that we have an HCl, all of it is being attached. All of it is being attached. The bond over here is broken, and we have an H attaching where? Basically, wait. Yes, we have an H attaching here, okay, because it becomes CH2. We have a Cl attaching here, okay. Clearly, what we should be more interested in is the Cl attaching over there, because an H uh, doesn't really make a huge difference unless sometimes it's substituted. But when H alone is added, we don't really look at it as a, oh my god, okay. So Cl minus H plus Cl minus clearly attacked over here. So minus, so it's a, oh wait, if it's a minus then it should be nucleophile, right? My bad, my bad. Then, okay fine, see, I'll be honest with you guys, I don't know what's up with this question. You guys, if you guys know, let me know, help me out as well, okay. I'm being honest with you, I don't want to just say some random shit, waffle out, and I don't know. Being honest, anyone knows, let me know in the comments, okay. Sure, please let me know in the comments. uh, Look at this, pretty straightforward. Over here, H plus is a, what's happening here? Substitution reaction, of course, and we see that NO2 is attached. So wait, that's just me. Okay, wait. If this is H plus NO3 minus, and NO3 minus attacks that. But no, okay, no. Look at this. Sorry, I'm not gonna cut this out because you should know that I'm not like a know-it-all, okay? HNO2, so it's HNO3 splits into OH minus and NO2 plus, okay? That's how you get NO2, and that's how you get, yeah, one of the O's goes here and one of the O's stays here. So this is minus and this is clearly plus. This attacks over here. Since it's plus, it's electrophile, so electrophilic, okay? Is that what's going on here? Am I missing something? Honestly, this I don't know how to crack this. Please guys, help me out. Now, like I said, when we have stuff like Br2, Cl2, F2, H2, etc, 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 they usually undergo homolytic cleavage, which will result in the formation of radicals. So over here it's a radicular addition. So basically we see H splits into two, H and adds up here, radicals. Okay, same over here, our Cl by splits into two, okay. It goes one over here and becomes CH3Cl, and then goes another one and then forms an HCl. So clearly Cl has split into, so radical. These are MCQs which have the answers to them as well in the seminar. I hope you guys can solve that. I'm rushing a bit, I know, I realize that I am. The plan was initially to just, go to a lecture and then come back and make the videos right then and there. But of course, that didn't happen. and that's not really nice, but shit happens. Now I hope you guys can solve those questions by yourselves. If you have any doubts, please hit me up on Instagram or whatever at, wait, shit. Oh, what the hell? Wait. R underscore, yeah. That's my at. You can talk to me there. Message me if you want. Yeah, so if you guys have also, if I've made any mistakes, because I make mistakes. I do make mistakes. Please let me know. Okay? Oh, also, I said that, but don't just think that, oh, he makes mistakes, he just admitted it, I'm not gonna watch his videos. I don't usually make mistakes. I've made like 1 or 2 mistakes in all of my videos. So don't worry about that. I'll try my best to put all the organic chem videos. If you have any doubts, if you feel like I'm going a bit too fast, if you feel like, oh, you're not doing enough questions, you're not going through all of the questions, tell me. I will tell me in the comments. I'll improve. Okay. See you guys for the next video. For now, that's it. Let me just